Welcome and hello. I would like to do a quick review of some math and physics concepts, and the point of this is to help out those in the flat earth community to be able to be more quantitative and accurate in their statements. So beginning, I don't see so much that there are math mistakes. A math mistake would be something like 2 times 3 equals 5. That's actually a mistake. So you didn't follow the rules of math. And also in the physics side, it's not so much that the equations that are used are wrong. It's that they're applied in the wrong context. So math and physics together, and we get classical mechanics. This is the physics that lets us explain falling balls off buildings, shooting bullets, arrows, even up to the orbit of the moon. So let's begin. Newton's 3 laws. First law is objects at rest stay at rest unless acted on by an outside force. So at rest means this pencil will stay there until some force from the outside acts upon it. Right now it is in equilibrium. The tendency to fall down is countered by the tendency of the table to hold it up, and until something happens, it won't move. Object's second piece of that is objects in motion stay in motion. So as a hockey puck on an ice rink is a great example, because there's very little friction between the puck and the ice, and it stays going in a straight line unless something happens to it on its way. Another one would be coasting your bicycle. There's very little friction, and so the bicycle will coast for a long ways until another force is applied to it, whether that be brakes, pedal, a hill, a corner. Newton's second law is force is proportional to acceleration. So this is force. Here we have mass. And mass is the quantity of matter. Now, mass is not ever going to be 0 in our calculations. If the mass is not 0, then if the force is not 0, then the acceleration must also be not 0. Or if the force is positive, acceleration must be positive, because you also don't have a negative mass. This is important because if there is a force and there is a mass, there will be acceleration. We also talk about net force. And a net force is just like your net income. It's what's left of your income after all the deductions are removed. So we may have multiple forces in multiple directions that are added up, and that comes up with our net force. And it is our net force that causes acceleration. Finally, every action has an equal and opposite reaction. And that also is illustrated by the pencil balanced or in equilibrium on the table. And it also is described quite well with a baseball bat hitting a baseball. All right, what can we feel? This has been stated by many and correctly. We do not feel velocity or speed or motion. We feel changes. Speed, we feel changes if we speed up or speed down. Velocity is speed plus direction. We feel changes in velocity, whether it's a change in the speed we are going or if it's a change in the direction that we are going. We do not feel velocity, speed, motion. There's a lot of talk about the Earth hurling through space. Well, we don't feel the speed or the motion. We only feel the acceleration. And we'll get to that more. Net force, I already talked about. This next part is really where the confusion comes in. There are real forces and fictitious forces. A real force acts on an object, causing acceleration. So here's my very nice drawing of somebody on a merry-go-round. This merry-go-round is moving around. And if you are on the merry-go-round and it's spinning around, it will seem to you like you are being pulled or thrown off the merry-go-round. That's what it feels like. But in reality, the only force active in here is toward the axis of rotation or toward the center. There is a real force. So centripetal acceleration would be the force from the outer edge of the ring or circle that is spinning toward the center of the spinning object. The centrifugal, often this is pronounced centrifugal, the centrifugal acceleration is a fictitious force. It's apparent, which means that we can feel it. It feels like you're being thrown off the merry-go-round, when in reality, you're being pulled toward the center. This is rotational forces, rotational acceleration, and this is actually a little bit more complicated than straight line motion. Straight line motion, okay? So we're in a car, and we start at 0 miles an hour, miles per hour, and we accelerate to 60 miles per hour. What does it feel like when you're inside the car? I'll draw a little a seat here and a little person on it. All right, here's the accelerator. Good name for it. As the car accelerates from 0 to 60, everything in the car and the car itself wants to stay put. Objects at rest, stay at rest. When you mash the accelerator, it seems like you are being pushed back into the seat. There is an apparent force. You feel like you're being pushed backwards. If the seat wasn't there, you'd fly backwards. You're hanging on the steering wheel. But in reality, it is the car that is accelerating from 0 to 60 miles per hour, and it is your body that wants to stay at rest. Just add some color to my little guy here. So which direction is the force in this example of the accelerating car in a straight line? The force is in this direction. But because your body wants to stay at rest, wants to stay at 0 miles per hour, it feels like you're being pushed back, when in reality it is the seat which is pushing into your back and surging you forward. Opposite example. This car will start at 60 and decelerate to 0. This time, we have one of these things going on. Again, the seat and my very nice drawing. When you slam on the brakes, it feels like you are being lurched forward. This is when you get the kids laughing in the car because you slam on the brakes for no reason. But it actually isn't. There is no force pushing you forward. It is a fictitious force. It is an apparent force. We feel it, but it's not real. What is really happening is your body wants to maintain a 60 miles per hour smooth, constant motion. When the car begins to slow down, it is pulling backwards on your seatbelt and on your body. It feels like you're being lurched forward. That is the apparent force. The real force is the deceleration in the backwards reverse direction. That is the real force. Finally, going around a corner. Now this one's a little bit more difficult for me to draw. So this is kind of a sports car, and it's going around a corner at significant speed. It will seem like to the person in the car, and I'll just draw their head, it will seem like to the person in the car that they are being pushed toward the outside of the car as the car goes around this left-hand corner. This is when we sit in the back as kids and we play the game called corners, where when the car goes around the left corner, we all go with the tendency to slide to the right and push against our brothers and sisters and smash them up against the door. It feels like, so this is a fictitious force. It feels like you're being lunged to the left, to the right, when in reality, there is a force acting on you toward the left. This one is fake, fictitious, this one is real. If the forces do not zero out, there is acceleration. If these were both forces, they would balance out and there might be no acceleration. If these forces were both real, the car wouldn't slow down. If these forces were both real, they'd cancel each other out. So in this case, this lurching to the left can be described by, I tried this with my pencils, but they won't bend. Which way do I have to bend this in order to make the curve? I have to bend it this way. Which way is the force? Just like the green, I'm pushing this way. If the red was an actual force, then it would push on the straw and the car would go in this general direction. So the real force is to the left, even though we feel like we're going to the right. The real force is a deceleration, even though it feels like we're going forward. The real force is the seat pushing into the back of you, even though it feels like you're being pushed back into the seat. Also, with the rotation of objects. So here's an example of the Earth on its tilt, on its axis, and I will draw a figure up here standing on the North Pole. Would he feel motion or would he feel acceleration? So the question is, does this guy feel anything? Well, same example. Here's a merry-go-round. If you stand right in the middle and it's spinning, can you feel it? Well, the question is, how fast is it turning? The Earth rotates once every 24 hours. So if you were to stand in the middle of the merry-go-round and it rotated once every 24 hours, would you feel it? There's the question mark. Would you feel that? And the answer is no, absolutely not. It would seem like you're not moving at all. In fact, you'd move half as fast as the hour hand on a clock. So this person up here at the pole really has no acceleration happening to them, so they don't feel anything. The question, and I'm afraid the confusion, comes in with this fellow. Now they are spinning around as the Earth rotates. What do they feel? So again, a call out, and what do they feel? All right, that's it. Next time we'll pick up with rotational momentum, rotational forces, and go from there. Thank you for watching.